Hi, in this video, we are going to continue our discussion of hyperbola. So last class, we did some basic theory. We looked at standard equations of the hyperbola and also equations of tangent and normal. Today, we'll start off with the idea of director circle. So what is the director circle? As we have seen before, it is the point of intersection or locus of point of intersection of perpendicular tangents to the hyperbola. So we saw before earlier for parabola and ellipse also, the locus of point of intersection of perpendicular tangents is the director circle. For the parabola, it's not a circle. For the parabola, it was the directrix line, because from the directrix we can draw perpendicular tangents to a parabola. For the ellipse, it had come out to be the circle like this. This was a director circle with center same as the center of the ellipse. And we'll get a circle for hyperbola as well. So let's see how we do that. So equation of any tangent to the standard hyperbola x square by a square minus y square by b square equals to 1 is y is equal to mx plus minus root over a square m square minus b square. So there are two tangents with the same slope m. Now suppose point P x1 y1 is the required point of intersection. So P x1 y1 is the point of intersection of the tangents. In that case, the point P will lie on this tangent equation, and therefore we can convert it like this and write y1 is equal to mx1 plus minus root over a square m square minus b square. Now from here, we can square it. Y1 minus mx1 whole square is equal to a square m square minus b square, and make it a quadratic equation in m. If you simplify, this is what you get. Quadratic in m like this, minus 2x1 y1 m plus y1 square plus b square. This is after simplifying this expression, we get a quadratic in m. Now, if it is a quadratic in m, it can have two possible roots. And since it has two possible roots, those roots will be the slopes of the two tangents. So m1 and m2 are the two possible slopes of the tangents that can be drawn from Px1, y1, right? Now, because we want the tangents to be perpendicular, we can say m1, m2 should be minus 1. And that implies here product of the roots in this is y1 square by b plus b square by x1 square minus a square is minus 1. So if you cross multiply now, you will get y1 square plus b square is equal to minus x1 square plus a square. This becomes x1 square plus y1 square is equal to a square minus b square. And since this is a relation connecting the coordinates of the point P x1 y1, the locus of P would be simply x square plus y square is equal to a square minus b square. And this becomes the equation of your director circle. So director circle of a hyperbola has center same as the center of the hyperbola and radius of root over a square minus b square. Okay. Now we also have another circle associated with the hyperbola, which is the auxiliary circle. This is similar to what we saw in the ellipse. So if the equation of the hyperbola is this, the equation of the auxiliary circle is simply with the semi-major axis. So major axis means the transverse axis. So it will be x square plus y square is equal to a square. That is the equation of the auxiliary circle. The auxiliary circle looks somewhat like this. This is the situation. This is my auxiliary circle. Because this distance is 2a, which is the diameter of the auxiliary circle. The center of the auxiliary circle is same as the center of the hyperbola, right? Okay, the next concept is chord of contact. Chord of contact equation is obtained in a similar manner. If you have point P x1 y1, the equation of the chord of contact is x1 by a square minus y1 by b square is equal to 1. So basically we are putting the point x1, y1 and writing an equation as if we are drawing a tangent at that point. However, you have to understand what chord of contact really means. So what it means is, suppose there is one tangent here and another tangent here. This point is P, x1, y1, and chord of contact is from P you have drawn two tangents. This chord is the equation, is the chord of contact. Connecting Q and R, and Q and R are the points of tangency. Equation of this chord is x1 by a square minus y1 by b square equals 1. So this is similar to what we saw in the ellipse and parabola case as well, right? Okay. The next thing that I want to talk about is asymptotes to a hyperbola. So this is a very important idea. You need to pay attention and make sure that you understand this. Let's say we have a situation like this. This is my standard hyperbola, and these are the vertices 0, comma minus a, and this is, no, I'm making a mistake. It is minus a comma 0 here, and this is a comma 0. The center is somewhere here, and the conjugate axis vertices are here 0 comma b and here 0 comma minus b, right? So you can draw sort of a rectangle passing through these points. You can draw parallel lines at y is equal to b and y is equal to minus b, and x is equal to a and x is equal to minus a, and you get sort of a rectangle like this, right? This rectangle will become important when we talk about asymptotes. Okay. So first thing, what is the meaning of an asymptote? So the tangents of the hyperbola which touch the curve at infinity, points of infinity. Such tangents are known as asymptotes. Okay. So now let's think about how we will get an equation of an asymptote. So we know that y is equal to mx plus minus root over a square m square minus b square is the equation of a tangent to the hyperbola. Here, if this was the equation of my tangent and x square by a square minus y square by b square equals 1 was the equation of my hyperbola, then the point of contact or point of tangency, if you solve these two equations, the point of tangency comes out to be this, minus a square m by root over a square m square minus b square, comma, minus b square m by root over a square m square minus b square. This is the point of tangency of this tangent, right? Now, what you can say is that if a square m square minus b square is 0, then point of tangency tends to infinity. Tangency tends to infinity, comma infinity, because the thing inside the square root will become 0. So then the point of tangency will be infinite. So basically the condition for asymptote, which is a tangent at an infinite coordinate to the curve, is a square m square minus b square is 0, which means m square is equal to b square by a square, and m is equal to plus minus b by a, right? Now, if m is equal to plus minus b by a, we can draw a line through the center, which looks like this. This is one line, and this is another line. So this line is y is equal to b by ax, and this line is y is equal to minus b by ax. Notice the two slopes are plus minus b by a, right? These lines are our asymptotes. So basically, these are the diagonals of my rectangle, diagonals of the rectangle that I found with the vertices. So which rectangle? The rectangle using this point minus a comma 0, a comma 0, 0 comma b, and 0 comma minus b. The diagonals of those rectangle are y is equal to b by ax and y is equal to minus b by ax. And we know if the slope is plus minus b by a, then from the point 0, 0, the tangents will meet at infinity separation. So basically, these lines are known as asymptotes and they will touch the curve very far away, right? So you have basically two asymptotes, and the two asymptotes are given by y is equal to plus minus b by ax. So you have basically y by b is equal to x by a, or y by b is equal to minus x by a. So you can write it as x by a plus minus y by b equals 0, right? So these are the two asymptote equations. So if you write them as a pair of asymptotes or a pair of straight lines equations, so basically combine both the equations of the asymptotes as a product, and that will give you the pair of straight lines equations. You will get x square by a square minus y square by b square equals 0. This is the equation of pair of asymptotes to the hyperbola x square by a square minus y square by b square equals 1. So that is something that you should remember. Now notice one important thing. Equation of the hyperbola was this. Equation of the pair of asymptotes is this. And equation of the conjugate hyperbola is this. So notice these three equations all differ by a constant. Differ by a constant. If you write the equations like this, x square by a square minus y square by b square minus 1 equals 0. And here x square by a square minus y square by b square equals 0. Here it will be x square by a square minus y square by b square plus 1 equals 0. So notice that in this equation, I am doing a plus 1 to get from hyperbola to asymptote equation. And the same plus 1 if you do, you get from asymptote to conjugate hyperbola equation, right? So the equations of the asymptotes and the hyperbola differ by a constant, and the equation of the conjugate hyperbola and the asymptote will differ by a same constant, the same constant, right? So you can also call, if you call this equation as h, the hyperbola, this equation as the asymptote equation, and this equation as h dash, which is the conjugate hyperbola, you always have this relation, h plus h dash is equal to 2 times a. This relation will be true because they are differing by the same constant always, right? Another thing to notice is the asymptotes were like this and the hyperbola was like this, and the slope of the asymptotes was this angle theta. Tan theta was equal to b by a, and again here also the slope was minus b by a, so this angle was also theta is equal to tan inverse b by a. So basically what we are saying is that the two asymptotes are equally inclined with the axis of the hyperbola. What that means is the transverse axis is the bisector of the two asymptote lines. Similarly, the conjugate axis is also a bisector of the two asymptote lines. So that is a very important idea. And also one more thing, asymptotes always pass through the center of the hyperbola. Asymptotes always pass through the center of the hyperbola. So if you remember these things, I think you should be fairly sorted in order to solve problems on these. So next thing that we will look at, okay, one last thing I can tell you here, the angle between the two asymptotes is 2 theta. This is the angle between the two asymptotes, and that is 2 times tan inverse b by a. That is obvious because we know the equations of the asymptotes are y is equal to b by ax and y is equal to minus b by ax. You can check the angle between these two lines, and it is always going to be 2 theta, which is 2 times the tan inverse of b by a, right? Okay, now what we will do is the parametric representation of points on a hyperbola. Parametric representation of points on a hyperbola. So if you have x squared by a squared minus y squared by b squared equals 1, the parametric representation for any point on the hyperbola is a sec theta comma b tan theta. Why? Because if you put a sec theta comma b tan theta in this, you will get sec square theta minus tan square theta equals 1, which is true by identity. So that means that any point of this form always lies on the hyperbola. Now, why is this important? Because right now we have, if we have to take a random point on the hyperbola, we could have taken p x1 y1, or we could have taken this. If you take the parametric form, you are using only one variable theta. Whereas in p x1 y1, you have two unknowns x1 and y1, right? So parametric form sometimes helps in solving problems easily. It makes it easier to solve problems. Now, what is this theta angle? Which angle is this theta in the diagram? You need to understand that very carefully. So if I draw a hyperbola like this, this is the vertices of the hyperbola. So minus a comma 0 and a comma 0. I can draw an auxiliary circle of the hyperbola here. The auxiliary circle will have center 0, 0 and will have diameter 2a, right? Now, take a random point on the auxiliary circle. This point is at an angle theta here. And this point, since the radius of the circle is a, it will be a cos theta comma a sin theta, right? And from this point, draw a tangent to the circle. So draw a tangent like this. This is point P and this is tangent PT, right? This tangent will intersect the major axis at some point here. Let's find this point N, okay? Now, first of all, in order to draw the tangent equation, I need circle equation. Circle equation is this. And obviously, tangent equation becomes x into x1, which is a cos theta, plus y into a sin theta is equal to a square. So the tangent equation is x cos theta plus y sin theta equals a, right? Now, where will this line meet the major axis or the transverse axis of the hyperbola? That is happening at y is equal to 0. So x will be equal to a by cos theta, right? So this point would be a sec theta comma 0, right? Now from this point, you have to draw a perpendicular to the transverse axis. So this is 90 degree and find the point where it intersects the curve P dash. So notice that if you have n as a sec theta comma 0, then this point also has a sec theta here. And if you put it in the equation of the curve, x square by a square minus y square by b square equals 1, if x square by a square minus 1 times b square is y square. So therefore, when you put a sec theta here, it becomes x square theta minus 1 times b square is y square. Y is equal to plus minus b tan theta, right? So you are getting this point on the vertical side, on this positive y side is a sec theta comma b tan theta. So understand that the point on the hyperbola a sec theta comma b tan theta is such that this angle from O to P is not theta. You don't need to confuse this angle with theta. This angle is some other angle alpha, right? The angle theta is referred to a point on the auxiliary circle at which you draw a tangent which meets the transverse axis at n, and then you draw a perpendicular and find this point, right? So this angle alpha is actually tan alpha is equal to b tan theta by the base, which is a sec theta, right? So tan alpha is equal to sine by cos, so it is b by a sine theta. So that is something that you need to be aware of, right? Okay. So, right. So that explains our parametric point. A parametric point is constructed using the auxiliary circle and then drawing a tangent to the auxiliary circle, intersecting it with the transverse axis of the hyperbola, and then drawing a line perpendicular to the transverse axis passing through that point of intersection that we just found. That will give us the point on the hyperbola corresponding to the eccentric angle theta, right? Okay. The next idea is the idea of chord joining two points alpha and beta on x squared by a square minus y squared by b square equals 1. So basically, this is two different points on the hyperbola, which is a sec alpha, b tan alpha, and another point is q, which is a sec beta and b tan beta. Now the line joining PQ, line joining P and Q is the chord of the hyperbola. And we can find that by first finding the slope of that chord, which will be B tan beta minus B tan alpha by A sec beta minus A sec alpha. This becomes M is equal to B by A. This becomes sine by cos minus sine by cos. So it is sine cos. So it will be on top, you will get a sine of beta minus alpha. And you will get a cos beta cos alpha. And in the denominator, you get a 1 by cos minus 1 by cos. So it will be cos alpha minus beta. Cos alpha minus cos beta by cos alpha cos beta. So cos alpha cos beta will get cancelled and you will have this expression. Now you can simplify this by using half angle formulas. B by A, you can write the top part as 2 sine beta minus alpha by 2 cos beta minus alpha by 2 divided by cos C minus cos T is 2 sine C plus D by 2 alpha plus beta by 2 sine D minus C by 2. So this is sine beta minus alpha by 2, right? This part gets cancelled, 2 gets cancelled, and you are getting slope is B by A cos alpha minus beta by 2. Because cos is even function, we can replace beta minus alpha by 2 and write it like this, divided by sine of alpha plus beta by 2. So once you get the slope of the chord like this, you just have to use the 2-point form equation to simplify it and write the equation of the chord. Again, the simplification is a little annoying, but you need to remember the equation of the chord joining two parametric points on a hyperbola. This chord equation can be written like this. X by A cos of alpha minus beta by 2 minus y by B sine of alpha plus beta by 2 is equal to cos of alpha plus beta by 2. So this chord equation has to be remembered because you don't have time in the exam to make simplifications like this. I am showing you how to do it. You are getting M is equal to this, and then you use any one point and slope is known. So point slope form will give you the equation. But the correct form of the equation, the standard form of the equation only comes after you do a little bit of trigonometric manipulations, right? Also, if this is a chord equation connecting two random points, we can also find the condition that this chord is a focal chord. So the chord equation is x by a cos alpha minus beta by 2 minus y by b sine alpha plus beta by 2 is equal to cos of alpha plus beta by 2. What if this point passes through the focus AE, 0? This chord passes through the focus AE, 0. So let's put AE here. You'll get E cos alpha minus beta by 2 is equal to 0 here. So this term vanishes, is equal to cos of alpha plus beta by 2. Right? And now we can write 1 over E as cos of alpha minus beta by 2 divided by cos of alpha plus beta by 2. Right? And if you do componendo and dividendo, 1 minus e by 1 plus e will be equal to cos of alpha minus beta by 2 minus cos of alpha plus beta by 2 divided by cos of alpha minus beta by 2 plus cos of alpha plus beta by 2. And using the half angle formulas, you should realize that this top part is 2 sine alpha by 2, sine beta by 2, and the denominator is 2 cos alpha by 2, cos beta by 2. So what we are getting is 2 get cancelled, and we are getting the condition that tan alpha by 2 times tan beta by 2 is equal to 1 minus e divided by 1 plus e. So that is the condition for a chord to be a focal chord. A chord connecting 2 points alpha beta is a focal chord if tan alpha by 2 into tan beta by 2 is 1 minus e by 1 plus e. So that is super important. Now what we will do is we will do the tangent and normal equation in terms of the parameter theta. So tangent and normal in parametric form. So since our parametric point is a sec theta b tan theta and the equation of the curve is x square by a square minus y square by b square equals 1, the tangent equation will become x a sec theta by a square. So x sec theta by a minus y tan theta by b equals 1. This is my tangent equation, and you can see that the slope of the tangent is minus of sec theta by a divided by minus of tan theta by b. So this becomes b over a 1 by cos, and this is sine by cos. So this becomes 1 by cos and sine by cos. So you are getting b by a sine theta. That is the equation of your tangent or slope of the tangent. So slope of the normal would be basically, we actually don't need to write it in sine and cos actually. It will be better if we keep writing it as sec and tan only. So here only we can say the slope of the tangent is b by a sec theta by tan theta. So slope of the normal would be minus of a by b tan theta by sec theta. And if you know the slope of the normal, you can write the equation of normal as y minus b tan theta is equal to minus of a by b tan theta by sec theta multiplied by x minus a sec theta. And if you simplify this equation, you will get eventually this equation ax by sec theta plus by by tan theta is equal to a squared plus b squared. This equation becomes your equation of normal in the parametric form. So this is my tangent equation in parametric form, and this is my normal equation in parametric form. Okay. Another condition that you can figure out now, we saw this condition earlier. So condition that line Lx plus my plus n equals 0 is normal to x square by a square minus y square by b square equals 1. So how do we do that? Let's say the point of normal, point where it is normal is a sec theta b tan theta. So equation of the normal to the hyperbola here is ax by sec theta plus by by tan theta is equal to a square plus b square. And we know that Lx plus my equals minus n is also the normal. So these two things represent the same line, represent the same normal line. So since the two line equations represent the same normal line, we can compare coefficients and we get a by sec theta divided by L is equal to b by tan theta divided by m is equal to a square plus b square divided by minus m, right? From these equations, we can easily eliminate, because we can eliminate and find sec theta. Sec theta would be minus na by a square plus b square into L. And tan theta would be minus nb by a square plus b square into m. So once you have gotten sec theta and tan theta, we can use the identity sec square theta minus tan square theta to eliminate theta, right? And finally, when you do that, the condition for normal lines is becoming a square by L square minus b square by m square is equal to a square plus b square whole square divided by n square. This is the condition for this line Lx plus my plus n to be normal to the hyperbola, right? Okay, so now that's about it for the standard hyperbola. We can also look at the special case of a rectangular hyperbola now. So what is a rectangular hyperbola? So basically, x square minus y square is equal to a square is a rectangular hyperbola equation. Here, a square is equal to b square and e is equal to root 2. We saw that briefly earlier, right? Now notice that if this is my rectangular hyperbola equation, the equation of the asymptotes will be y is equal to plus minus x, because usually it is plus minus b by ax, but in this case, b and a are equal. So these are my asymptotes, right? Now, this rectangular hyperbola looks somewhat like this. This is my rectangular hyperbola. These are my asymptote lines. X square minus y square is equal to a square. However, what you can do is you can find the equation of the rectangular hyperbola whose asymptotes are the x-axis and y-axis. So right now, y is equal to x and y is equal to minus x are my asymptotes. I can find in hyperbola where the asymptotes are not y is equal to x and y is equal to minus x. These are basically the x-axis and y-axis. So this is my new y-axis and this is my new x-axis. And if you imagine a rotation, so basically now I'm going to look like this. My hyperbola equation becomes like this. This is my hyperbola, right? What I have done is I have taken the original y and x axis and I have rotated it this side by 45 degrees, which was this angle, right? So my new y dash x dash is the new axis and the axis is the asymptote lines. This axis is the asymptote itself. But the curve equation will also start looking different now. So how do we do this rotation? There is a standard theory of rotation. I have covered it before in my channel. You can check out the videos in the same playlist. There is a video on rotation and transformation of axis. Okay. You check it out, understand how to do rotation. If you do the rotation, the equation of the hyperbola will also change. And in order to do the rotation, you have to convert x comma y in the original to capital X, capital Y after rotation. So the equations connecting these variables are x is equal to x plus capital Y by root 2 and y is equal to x minus x plus y by root 2. If you don't understand how to do rotation, check out the videos in the playlist here. So there is a video on rotation and transformation of axis. You need to go through that. We might cover it later when we do straight lines again. Okay. So then in this case, the equation x square minus y square is equal to a square will now become x is x plus y whole square by 2 minus this is y minus x whole square by 2 is equal to a square. And now this will start looking at x plus y whole square minus this is becoming 4yx, right? is equal to 2a square. So you're getting xy is equal to a square by 2. And if we call a square by 2 as a constant c square, we get the new equation xy is equal to c square. And that is an alternative way of looking at a rectangular hyperbola. So that is a different equation. Here c square is clearly a square by 2, right? So both of these equations, x square minus y square is equal to a square, and also xy is equal to c square, where c square is equal to a square by 2. They represent the same hyperbola, the same hyperbola. The only difference between the two is that here the asymptotes are the lines y is equal to plus minus x, and my y-axis and x-axis are like this. Y is equal to x is my asymptote, and this is y is equal to minus x. This is the normal rectangular hyperbola graph. But after rotation, you will get a new situation where asymptotes are, this is my new y-axis and x-axis. The asymptotes are themselves the y and x-axis. So what I have done here is taken the original axis, y and x, and rotated it by 45 degree to come up with a new axis, y dash and x dash. And both my axes have been rotated by 45 degree in the clockwise direction, right? In that case, the equation of the curve now becomes this, where c square is equal to a square over 2, right? The hyperbola is still a rectangular hyperbola. It still has eccentricity of root 2, right? Now, similarly, you can understand that we can find the equation of hyperbola having x is equal to alpha and y is equal to beta as its asymptotes. So far, when we look at a rectangular hyperbola, our asymptotes are x is equal to 0 and y is equal to 0. We can make an equation of a hyperbola with this as the asymptote. So first of all, what you can say is x minus alpha equals 0 and y minus beta equals 0 are the equations of asymptotes. Now, if you multiply these two equations, it gives us the product of these asymptote lines, and this is the equation of pair of asymptotes. Now, what you can do is, we know that the equation of the hyperbola and the equation of the asymptotes differs by a constant. So, what we can say is, if this was the equation of my asymptotes, the equation of the hyperbola would be the same equation plus some constant. X minus alpha, y minus beta plus gamma equals 0 is the equation of my hyperbola. So if you have the equation of pair of straight lines representing the asymptotes, you can always add a constant to it and get the equation of the hyperbola. How to find the constant? You can check whether this equation satisfies the conditions of being a hyperbola. Basically, you should check del should not be 0 and h square minus ab should be positive, right? And if it is a rectangular hyperbola, e will be root 2 also. So that is also something that you can remember. Now, suppose we have rectangular hyperbola equation like this. Here, the parametric points for this hyperbola can be taken as ct and c by t. And you can follow the same methods that we did earlier to find all of the things that you need. For example, equation of chord would be the line equation connecting ct1 comma c by t1 and another point ct2 comma c by t2. So you just take these two parametric points on the curve and draw the equation between them. When you solve it, it will come out to be like this: x plus y t1 t2 minus c t1 plus t2 equals 0. You don't need to remember this. You can just do it by common sense here. Write down these two forms and solve it using that, right? The equation of tangent would be, how do we obtain that? We can say by the replacement method, 2xy was replaced by x1y plus xy1. So xy is replaced by an x1y plus xy1 by 2 is equal to c square. So you get x1y plus xy1 is equal to 2c square. And for x1, we will put ct1 by and c by t1. So we will get ct1y plus c by t1x is equal to c square, 2c square. This c gets cancelled. And finally, the tangent equation has come as t1y plus x by t1 is equal to 2c. Again, no need to remember it. As long as you know the general process, you will be able to find it yourself, right? So the standard method that we have learned for all of the hyperbola and all of the other conic sections, everything is still valid. You just need to use the parametric points Ct and c by t when you do it, right? So that finishes off the theory, the important ideas that you need for hyperbola. Now, from next class onwards, what we'll be doing is conic sections, combined and mixed problems on all of the three topics, just so you are very comfortable with the entire chapter. We'll probably do 2-3 videos on conic section, maybe 1 or 2 videos on problem solving for all conics. And after that, we'll go on to circles and straight lines. That's it for this video. I'll see you next time.